Presentation today. The presenter for today is Mr. Erman Gungor from Middle East Technical University, one of our students, master's students, doing his research work on numerical modeling, finite element modeling. And his title is Adjustment Factors for MEPDG Payment Responses, considering 3D implications, analysis implications of white-based tires, basically. And as I understand from the short abstract, you've done work with the MEPDG comparisons and finite element abacus runs to check. So it'll be quite an interesting talk indeed from a material characterization and analysis and solution point of view. I look forward to, and we all look forward to your presentation, Erman. Thanks.
Hello everyone, my name is Erman. I am a second year master's student working with Professor Imad Al-Kadi. Okay, today I will be talking about developing adjustment factor for MEPDG payment responses, considering three-dimensional analysis and white-based tire effects. Here's my outline. First, I will briefly talk about the H2 payment design background and how MEPDG was developed, and then I will talk about the MEPDG design guide itself, and then I will speak about how we solve this problem, how we solve limitations of MEPDG, and then I will share results, and I will also do some discussions about the results that I will be showing, and finally I will finish my presentation by giving some conclusions. Till the mid of 20th centuries, there was no, world is lacking the published and comprehensive payment design guidelines. Because of this fact, the Highway Research Board approved construction of a new test section in Ottawa, Illinois in 1955. Ottawa, as you see here, it is north of the Rantoul, and it's somewhere between Rantoul and Chicago. And this test section was open to traffic in 1958, and the test started at the same time. There were 4 design guides were developed based on Escher road tests. First design guide was 61 interim guide. Then they revisited and reviewed 61 design guide, and they published another one in 72. And then again they modified the equations given in 72 interim guide, and they published another payment design guide in 86. So there were some modification between these 3. For example, in 86, they started considering resilient modulus for subgrade for payment design guide, and finally in 93 they finalized this, and they published 93 H2 payment design guide, which is still popular throughout the world, and still it's used a number of states in this country in the United States. And this is the final equation which is given in 93 H2 payment design guide. As you see, this equation is purely empirical, which means that it's coming from the regression analysis. And as you see, all the design guide between 1960s and mid 1990s were like empirical based design guides. So what is the advantages of using empirical based design guides? First of all, they are very time efficient. You have only one equation, and considering the computer power that we have today, it is very easy to solve them. And the other one, they are very easy to implement and use. As you see, there are only one equation with like couple of inputs, and they are very easy to implement and solve these equations. But what's the disadvantages of these empirical based design guides? Why we are trying to switch to mechanistic based design guides? The reason is that they are applicable only to conditions similar to those for which they were developed. What I'm saying, for example, I will be talking about it detail in following slides. But for example, you conducted test in one particular climate zone, and you want to make a new design in another climate zone. In that case, you are sort of doing extrapolation that we want to avoid when we are doing payment design. By saying that, now I will like to talk about the conditions existed in H2 road tests. Obviously, it only considers one climate zone, which is the Illinois climate zone. very limited sets of material. It has only 7.75 inch and 1 inch asphalt layer thickness. I mean, when you consider the pavement design which we are using today, you can tell that we are extrapolating a lot. And then they have only four different types of base material. Only one type material for subgrade, which was, I believe, A6 or A7, and limiting traffic volumes. Like when you think the traffic volumes back in 1960s and when you think the traffic volumes that we are having right now, you can say that there are really big difference between those. And axle loads have been increased, and new technology for tire types. Now we have white base tire in addition to dual tire assembly, totally new construction methods, and so on. So this road test basically shows that the condition existed in actual road tests were very limited, and most of the time that we are designing new pavement using this empirical based the methods, we are doing extrapolation that we want to avoid. Therefore, the need for new advanced design guide was recognized in 1968 by the agencies and the engineers, and then NCHRB project 137A was launched in 1998 under the sponsorship of the FHWA, NCAP, and ASHTO. And after 6 years of work, in 2004, they released the mechanistic empirical pavement design guide. And after this, the new projects 140A, 140B, and 140D were reviewed and revised MEPDG, which resulted in a new pavement design software, which later known as a Darwin ME, and the new, I will say, like improved version of the existing MEPDG design guides called MEPDG and Manual of Practice. This design guide is mostly developed for developing a computer software here. And finally, in 2013 August, they changed the name as the ASHTO Pavement ME Design Software instead of Darwin ME. And I'm hoping that they're gonna stick with this name. So after giving the brief history about MEPDG development, now I would like to talk about the MEPDG itself. So MEPDG stands for, as I said before, Mechanistic Empirical Design Guide. Mechanistic means that we are solving the pavement system by using the theories, and then we are calculating the distresses by using some empirical equations. This is the flow chart of the MEPDG. So basically, it takes all kind of inputs, structure, materials, environment, and traffic, and then it calculates structure responses considering these inputs. This box is means that stands for or refers to mechanistic part of the design guide, and then using the transfer functions which are empirical, we are calculating or predicting the distresses, which refers to the empirical part of the design guide, and then we are checking the design criteria, and we are keep iterating this flowchart until the design requirements are satisfied. So for the sake of this study, we are interested in this box here, structural responses, because as seen from the figure, like predicting structural responses is very important to predict the overall performance of the pavement. Because if you make a mistake here, naturally it's going to contaminate all rest of the pavement design guide. MEPDG has really theoretically sound and ground methodology and procedure to compute the structural responses, but still it has some limitations and unrealistic assumptions, which may lead to inaccurate, I will say, response calculations. Before talking about the limitations of MEPDG, I would like to explain the mechanistic part of the design guide, how it works for the flexible pavement, of course. First, it starts with the subdivision. Basically, you give your pavement structure to MEPDG, for example, 3 inch of AC layer, 6 inch of base layer, and so on, and it subdivides it into smaller pieces. The reason of this is to account for the temperature and aging gradients. And after this, dynamic modulus are calculated at the midpoint of each sub layer, considering velocity and temperature. I would like to take your attention to wording that I have been using. The aging, velocity and temperature. So it should remind us of the term of viscoelasticity, which means that MEPDG recognized the fact that the asphalt concrete shows the viscoelastic properties. And after having our subdivided pavement structure modulus, calculated modulus, then it runs to Julia, which is a linear elastic theory computer software, just like BISA, just like MN layer, KN layer, and so on, by also considering the other inputs such as loads. So as you see, the mechanistic part of the design guide is not only running the Julia here. It subdivides, calculates the dynamic modulus, and after this, it runs to Julia. So it has really well and theoretically sound procedure to calculate pavement responses, but still it has some limitations. I will talk about the limitations of MEPDG by comparing MEPDG with the finite element analysis. First of all, analysis type. I said that MEPDG implicitly considers viscoelasticity, but still it runs the Julia, which is the linear elastic software, and it doesn't consider the motion of tire. Basically, it assumes that the tire is steady and it's not moving, which is not real, of course. And tire type, because of the contact area that it is assuming, it can only consider real tire assembly. It cannot capture the white-based tire effect on contact stresses. Contact stresses, it only assumes that 2D uniform pressure, but we know that in the real life, tire applies 3D contact stresses in vertical, longitudinal, and transverse direction, and these stresses are not uniform, they are non-uniform. Contact area in MEPDG, it's assumed as a circular. Basically, it's calculated dividing axial load by the tire pressure. But in finite element analysis, we are our contact area that we are considering in finite element, it is true measured tire contact areas. Friction between layers in linear elastic theory, so MEPDG procedure assumes that the distributed spring model to model the interaction between the layers. But in the finite element analysis, we are using a model called elasticity model, which is able to simulate what is really happening in at the interface between the layers. And finally, the AC layer material properties, it also uses master curve, but to be able to get the complex modulus, you have to calculate the frequency, and MEPDG has a procedure to calculate frequency of loading. But as proved in two of the Professor Al-Qadi's paper, this procedure to calculate the loading frequency has some limitations, which results up to 140% error. So until this point, I try to explain why we need to modify the mechanistic part of the pavement design by explaining the limitations of them. Based on the fact that what I have just said, the objective of this study develop adjustment factors which modify the pavement responses obtained from MEPDG procedure and accordance with the results from finite element analysis, where we believe that we model the tire pavement interactions more realistically in terms of loading conditions and material characterization. An approach that we came up with dividing the limitations into two groups, one for the model complexity regarding the material characterization and loading condition, and the other one is incapability of simulating white-based tire. This flow chart demonstrates our research approach. We are going to develop two adjustment factors, one for the converting responses from real tire assembly to white-based tire, and the other one accounting for the model complexities and limitations in MEPDG procedure. Now I will start talking about the development of each adjustment factor, and I will share the discussions and results. Before starting talking about the adjustment factor one, I would like to take a moment and thank my research colleagues, Jaime and Angeli, because the finite element analysis have been run by them. I only implemented MEPDG and run those cases in MEPDG procedure. The total of 240 cases for white-based tire and real tire assembly have been run in Abacus considering same material properties and pavement structures. And the only difference between these two cases are contact stresses and contact areas, which were again measured under the same axial load and tire pressure. Why they are resulting in different contact stresses? Because of the structural difference in dual tire assembly and white base tire. We developed adjustment factor for like total of 8 responses, compressive strain within each layer, tensile strain at the bottom of AC, shear strain within each layer. But because of the time limitations and for the sake of brevity, I will be only showing like 4 of them. This is transverse strain at the AC surface. The y-axis shows the dual tire assembly. The x-axis, y-axis shows the white base tire. And here we have 2 lines. One is light green, the other one dark green. Light green here is basically unity line. It shows the y, basically y equals to x. I put this line to give you an idea that how significant to apply correction factor on the response. In other words, this gap, this difference between these 2 lines is interpretation of these coefficients of x here. So what I'm saying, for example, if you check the coefficients of x, you will understand that the white base tire is generally resulting in higher responses than dual tire assembly, and by the factor of about 1.5. And this is transverse strain at the bottom of AC. Again, we have a good correlation, and again, white base tire is resulting in higher responses than dual tire assembly. This is compressive strain within the base. Again, we have, as you see, the correlation is increasing as I go to deeper the pavement. This is because of the fact that when you go deep from the pavement, the effect of non-uniform tire contact stresses is diminishing, and the axial load is becoming governing factor in responses. That's why we are having more and more like higher and higher correlation between these 2 data, and the coefficients of x also decreasing when we are going deeper. And again, I will repeat the reason behind it, because when you go deeper in the pavement, the governing factor in responses becoming axial load, which is same for 2 cases. What is different between these 2 is contact stress distribution, which lose its effect when you go deeper in the pavement. And this is another demonstration of what I just said. Again, this is the shear strain within the AC, which occurs 1 inch below the surface, and as you see, the correlation values dropped down, and the coefficients of x increased, comparing the compressive strain within the base. So this finalized my results about the adjustment factor 1, which converts white base tire responses into, which converts dual tire responses into the white base tire responses. Now I will be talking about MEPDG adjustment factor 2, which accounts for the model complexity. For this adjustment factor, only dual tire cases are considered, because one more time, white base tire effect cannot be captured by the MEPDG. A total of 36 cases have been run in Abacus for dual tire assembly, and same cases have been simulated in MEPDG. Here I want to say that running the same simulation in finite element and MEPDG is very important for the sake of the accuracy of this study, because we want to have the consistent input between these 2 approaches so that we can compare the apple and apple. What I am saying, for example, we have to apply same axial load in finite element and same axial load in MEPDG so that we can compare the results and we can come up with the adjustment factor. For axial load, for example, when we are measuring the contact stresses, we are applying axial load and tire pressure, and we are using this axial load and tire pressure as an input in MEPDG. Contact area, this for finite element analysis, it is measured, and for the MEPDG, it's basically calculated dividing axial load by the tire pressure. Motion of tire in finite element analysis, we are moving the tire by the velocity of 5 miles per hour, and we are considering exact velocity when we are calculating complex modulus in MEPDG. Temperature, we are using basically the same temperature profile in both finite element analysis in MEPDG. That was the hardest conversion that I faced, the converting elastic stick model into the distributed spring model. I don't want to go into the details, but if you want, we can discuss about after the presentation. And the material properties, basically we use same master curve, same linear elastic moduluses for base and subgrade. So I was able to convert the finite element inputs to MEPDG, but the problem, like I had two choices. One of them is using the H2Ware software to get the responses, and the other one implementing the MEPDG as a standalone code in my computer by using the computer languages. And I chose to implement MEPDG procedure as a standalone tool because of two reasons. First of all, running 576 cases in software is time consuming and not feasible. What I mean by not feasible, if you use the MEPDG software, you will see that it considers track types, all loss spectra, and so on. But for the sake of this analysis, all I need applying one axle load and one tire pressure. So I don't need to go and get all this loss spectra data for each track type. And the second reason is, which is more important, this software only gives the critical pavement responses used in transfer functions. However, we are also interested in other responses such as shear strain within the AC pavement layer, because it is believed in the literature that the vertical shear strain might be the main cause for having the top-down cracking instead of the tensile strain at the AC surface. So I implemented the MEPDG as a standalone MEPDG procedure as a standalone tool, and I ran the simulation, and I faced some issues. The issues was differences in loading conditions and in general in the model introduces serious challenges to complicate development of adjustment factor 2. And to obtain statistically good correlation for adjustment factor 2, the cases were divided into thick pavement, thin pavement with strong base material, and thin pavement with a weak base material. Now I would like to remind that when I was developing adjustment factor 1, I didn't group the responses based on pavement structure like thin pavement, or based on the material characterization such as strong and weak. But for developing adjustment factor 2, I had to do that because of the challenges that introduced by differences in models. Now I will show the adjustment factor 2 results. Again, I have like in total like 30 plots for this adjustment factor 2, but I will be showing like 4 or 5 of them. This is the tensile strain in transfer direction at AC surface for the thick pavement. Here I obtained good correlation because of the fact that if you go and check the linear elastic theory and try to find the location where has the maximum tensile strain at the surface, you will see that it occurs far away from the wheel pad, where the governing factor in response is the axle load, not the contact stresses. That's why I have a relatively good correlation, and I would like to take also your attention to these coefficients here. It is 3.5, which means that finite element is resulting 3.5 times higher responses than MEPDG. This finding is matching what's found in the literature, because we know that due to some numerical implementation of the linear elastic theory, the linear elastic theory results inaccurate responses for tensile strain specifically for the surface, and this shows how linear elastic theory underestimates the tensile strain at the AC surface, which is important because currently in MEPDG, tensile strain at the surface used to predict the top-down cracking. That's why it is very important, one of the important responses. The second graph is tensile strain in transfer direction at the bottom of AC for, again, thick pavement. One more time, when you go deeper in the pavement, the effect of non-uniform tire contact stresses is diminishing, and we can see this observation here in the correlation factor by having it higher than before. Here, if you see the coefficient of X, you can tell that, like, for specifically for this response, there is not much of difference between MEPDG and finite element analysis, and the reason is what I have just said. Tensile strain, and I have very similar case for the thin pavement. Before the previous, this one was thick pavement, and this one for thin pavement, and pretty much same trend is being observed. Only difference is having the lower correlation of the R square value, and the reason, again, the effect of non-uniform contact stresses. And this is the compressive strain within the base for the thick pavement. I have relatively higher R square value, and the reason is, again, the governing factor in response is axial load rather than contact stresses. So this I like to remind us something about our finite element analysis. For the thick pavement, we consider base as a linear elastic material. On the other hand, for thin pavement, we consider this as a nonlinear material. So I would like to take your attention to the coefficients here. Before it was 0.65, which means that MEPDG is resulting higher responses than finite element analysis, but here it's 4. Which means that finite element analysis resulting 4 times higher responses than MEPDG. This finding is also matching with the literature, because in the literature it's said that considering base as a nonlinear material results higher responses if you consider it only linear elastic material. And these coefficients here shows the significance of considering base material as a nonlinear material. And the last plot is coming from the shear strain within the AC, with you can see very, very low with R square value. I put this plot intentionally to show one more time the importance of the considering non-uniform contact stresses in our pavement design analysis. MEPDG doesn't consider contact stresses, it only considers the 2D uniform pressure. On the other hand, as I said before, finite element, we are considering non-uniform contact stresses, and especially for shear in the AC, the effect of non-uniform contact stresses plays really important role. And if the top-down cracking is proved to be caused by the shear strain within the AC, it means that the MEPDG fails to predict top-down cracking accurately. So now I will quickly show the numerical example how this adjustment factor can be applied. So I choose the compressive strain within this subgrade. MEPDG calculates this response as 557 microstrain for this case here. And the adjustment factor 1 is given as this formula specifically for this response, and adjustment factor 2 is given here in this formula specifically for this response. So what these numbers means? So for example, this column shows that if white base tire was used instead of real tire assembly in our analysis, this response would jump to 670 microstrain instead of 557 microstrain. This column here, if we account for the model complexities, which is 3D non-uniform contact stresses, advanced interaction model, and so on, this response here will drop to about 400 microstrain, and this last column basically shows the combined effect of these two adjustment factor. I hope this slide clarifies how we can apply our adjustment factor numerically, and this picture shows our idea how this adjustment factor can be implemented in design software. Basically, there are like two tick spots can be put, and user can go and active one of these tick box based on if he wants to like consider white base tire effect or model complexity on effects of these two together. Now I will give my conclusion about my studies very quickly. We observed that for all the responses, white base tire produces higher responses than dual tire assembly, which means that it gives higher damage than the dual tire assembly. I don't know why it disappears. It doesn't disappear in my computer, but it's
Yeah, I can see it here.
I don't know. It's fine.
It's just the screen display.
It's fine. Adjustment factor can be applied without grouping pavement based on structure and material because, as you see, I had very high correlation values. The responses near the surface are significantly affected by non-uniform contact stresses which cannot be captured by MEPDG. Vertical shear in AC and tensile strain at the AC surface are the responses which are significantly underestimated by MEPDG, and these responses are important for us to predict top-down cracking. Considering nonlinear characterization for base material causes much higher responses. And adjustment factor should be applied considering pavement structure since the effect of non-uniform contact stresses differ according to thickness. I said this sentence maybe 1,000 times, but it is really important for our studies. And if you have any questions, I will be happy to answer them. I apologize if I was so fast. I don't know, it's my nature. I go so fast.
Questions?
Yes, thank you. I have a couple questions. You only talked about transverse strain. Did you calculate longitudinal strain?
Yes.
And that's less?
For which case, Professor specifically?
Just in general, bottom of the asphalt longitudinal strain.
For white base tire effect or model complexity effect? For white base tire, it doesn't matter. White base tire always produces higher responses than dual tire assembly.
And the strain's the same in both longitudinal and transverse?
No, they are not. They are not same.
So what's higher, transverse or longitudinal?
I don't know. But
You show. I guess maybe the plots you show are just a sample. Is that what I'm understanding?
Longitudinal. His question is.
Okay. Okay.
Okay.
That was my answer. Okay. 'Cause I always thought longitudinal was higher, and you're showing transverse.
What's the answer again for everyone?
I think, Erman, I don't think I can understand the question.
Go back to it's been the beginning.
Why did you not present horizontal strains? I think the question.
Longitudinal.
I mean,
I
longitudinal strains.
selected like one strain at the bottom of AC. I mean, I didn't have like specific reason not to present longitudinal.
Oh, okay.
I could have presented it.
Which one is more critical?
Basically, MEPDG gets whichever is higher. Like it calculates both, and whichever is higher, it gets it.
Generally, you get longitudinal, but sometimes you get the transverse in some occasions, but yeah.
We have both, like in our project, but I didn't put everything here.
That's fine. So it wasn't, you weren't just showing the worst case scenario. That's why I got confused.
Oh, maybe, yes, maybe.
Did you compare, you wouldn't compare any of this with standard single row tires, would you?
No, we have,
You're just doing dual tires with
Yes.
wide base.
yes.
So
You were talking about the steering wheel.
Yeah, or just any, maybe they don't have.
We didn't we considered only dual tire assemblies, and we didn't consider white base tire, which is one single tire in MEPDG, because we know that the contact stresses difference caused by white base tire cannot be captured by linear elastic theory. So I don't know
And
if
what you're
that's
talking about is outside the scope for this research.
Okay.
What Michelin does, we have varying tire parameters.
for the, yeah.
Yeah, that answer, we did steering wheel, but it wasn't part of this work, yes.
I guess the main emphasis then was how wide-based tire as opposed to the traditional dual, which is used in easel calculations, right?
Yes.
It's comparing.
You have kind of a narrow kind of scope right now. Okay. I did have one other question, sorry to, you said the tensile strain at the surface was primarily not correct because of layered elastic numerical analysis, was that?
Yes, I just reviewed that paper, Professor, actually. So it says that when they're implementing linear elastic theory in the software, because they observe some numerical
Instabilities.
Huh?
Instabilities.
instabilities to take this integration, which results in inaccurate responses.
Is that your reason, or that was what the paper said?
That was what the paper said.
So, because I'm curious, the difference is so large, I wouldn't think it's only because of that. Like, when you show the top tensile strength
Yes.
on the surface,
It was very.
you're saying like 4 times difference.
Yeah, like in linear elastic theory gives very small tensile strain at the surface because it finds it like very far away from the tire contact stresses. But in finite element analysis, we are finding like kind of closer to tire the wheel pad. That's why the difference is that big.
Yeah, I guess I would have come with a different conclusion. It's not the calculation error in layered elastic so much as the 3D contact stress accounting for a near surface tensile stress. That's how I read what you're doing.
Yes, maybe I should have said.
Because the tensile stresses are much higher just because you have this 3D contact stress at the surface that's generating much higher strain.
Yes. In finite element case, yes.
Okay.
But I was yes, it's correct.
All right.
Yeah. Well, that's a good point. I was thinking, well, you know where my question is coming from. Pavement based on the base course comparisons. At one point you said the thin versus thick, you were saying for the pavement base, right?
Yes.
In the thick one you considered nonlinear, and the thin one you didn't?
No, in thick one we considered base as a linear elastic because we have thick acid pavement, which we believe that it mainly carries the load.
Okay, I guess I got it wrong then. And then you were calculating responses in the middle of the layer in each case?
For finite element, we are basically finding the maximum.
Which is on top?
Yes.
Okay. The stresses are higher and everything.
Yes. I mean, we are,
Stress-dependent model you're using, right? Nonlinear?
yes, in finite element, what we are basically going through all the elements and we are getting the maximum the response which happens throughout the whole layer. But in MEPDG, it's always happening at the top of the layer.
What is happening at the top of that?
In MEPDG, in linear elastic theory, maximum compressive strain in base happening always at the top of the layer. But in finite element, it might not be the case because of the nonlinear base characterization. That's why we are going through all the elements and finding them.
I'm not sure how that contributes because the stress distribution, when you think about that, the stress-dependent modulus properties, there's one modulus versus modulus properties are quite higher towards the high, where the stresses are higher, like the stress ball, right? So modulus takes that kind of a shape, basically, modulus distribution in the base course when you look at that. So, and then I know in pavement, it usually goes into the middle of the layer to pick up the critical pavement responses and everything. Sometimes things can show up much higher in the top, and there's still debate on which location is the correct location to pick. For rutting of that base course, for example, where's the critical pavement response? Vertical stress on top of, or strain, whatever, like stress value, but right? Where'd you get that from? And how that affects the asphalt, because base is supporting the asphalt. So if there's higher modulus and better support for asphalt from the base, that's nicely correctly accounted for by nonlinear analysis, that will change your asphalt responses also, correct?
Yes, yes.
So those things are completely missing. There's a void out there now in Pavement ME on that because they just dropped the level 3 analysis, level 1 analysis. There's no, right. So, and
Actually, no, may I?
sure.
Yeah. Actually, this is that using the nonlinearity for the base layer is considered for the thin layer. So whenever we're dealing with thin layers, that's considered. But whenever we're dealing with very thick layer, we found that there is no difference because it's going to be very, very small stresses there. So the answer to your question, yes, we do, but for thin layers.
I see. Yeah. Well, again, he was showing some compressive strain in the base layer versus the effect of nonlinearity on the pavement response,
Right.
AC response, the HMA layer response. So those are two different things to look at. And the nonlinear and gross anisotropic and all those things, again, how one looked at that, Professor Al-Qadi's previous PhD student. And then Ming-Man Kim also looked at that with multiple wheel scenarios also for like gear wheel assemblies for airport pavements and things. So we have some couple good dissertations on that you probably need to look into.
I read a couple of papers, Professor, and all of them are saying that considering base as a nonlinear material results high responses than if you consider it as a linear elastic material. And this plot was kind of confirming this point.
So higher responses are bad or good?
I mean, in what sense? It's good that we are
Eventually linked to the life of the pavement.
Of course, it's bad.
Of course. So
Yeah.
it makes it critical.
Yes, yes.
So if we do better analysis and use wide-base tires, we have to build thicker pavement?
Say
Combine
that again. I'm sorry?
I said, what I'm concluding here is better analysis plus wide-base tires, thicker pavements.
Actually, no, Professor. White-base tires.
Yeah, basically.
If you consider only white-base tire,
Yeah.
you have to build the thicker pavement. But combining effect of these two is not clear. For example, this example that I showed here.
Yeah, but you were looking only at subgrade strain.
Yes.
But, yeah, you actually showed it go down there for subgrade.
Yes. So what I'm trying to say, combined effect is not like.
Depends on what's controlling, I guess.
Yes.
That's the depends. Is that what you're saying?
Yes.
Yeah. I think that's what you're saying. But if you're using a wide-base tire, surely the asphalt surface is higher, more stressed.
Yes.
But that may not result, I assume, in a thicker pavement.
So.
Does it actually result in a thicker pavement?
I mean, if like I'm considering we are having high responses because of real high assembly, which gives high damage. So we have to kind of control or reduce this damage problems. And one way is having the pavement, and the other way is having the asphalt is stiffer. So there are a couple of solutions to solve that problem.
So I think, let me put the question in a different way, if I may. So if you're going to have like a helicopter picture from the top here and look at it and say, okay, so which one's going to be performing better, the thin pavement or thick pavement when they are exposed to wide-base tire?
Thick pavement.
And the reason?
First of all, thick pavement, as I showed, like because of nonlinear characterization, it results higher compressive strain in base, which increases the rutting, which is one of the biggest problems. And I am not like this. The comparing tensile strain at the surface and the AC at the bottom of AC is not clear because thick pavement results in higher response at the bottom of AC, but on the other hand, thin pavement results in higher responses at the AC surface. So I will say again that considering the compressive strain within the base, I will say thick pavement will show better performance than thin pavement.
You know, just concentrating on the asphalt, the effects on asphalt and things. I know some former students compared, especially looking at just the tire and pavement contact, the wheel, the tire treads and things, and all the detailed finite element simulations, like June did some of that. And
Primate's doing it, Ms. Angeli.
so I thought comparing white base versus dual tire, the old, trucks that we had dual tire, it wasn't necessarily white base was more damaging, right? That's what I remember from previous
Actually,
research.
that's ultimately, was what my intention from the question. I guess if you are looking at it from the bigger picture, for thin pavement, the white base will be doing more damage. If you are going into the thick pavement, the damage will be definitely less. So you're going to look at it now, where is that the truck's going to be driving more and so on. So we did have some factors as to the damage for the rutting or fatigue or whatever. So, but in general, yes, the thin pavement, it's going to be more damage for the white base tire. Yep.
And pavement maybe doesn't
And of
have a
course,
chance,
it's
it
the type of
doesn't have
tire.
any
Yeah.
position to
White
be able
yeah.
to predict anything.
Yeah, and that's a big thing, actually. We didn't talk about it because now we're looking into the one that is marketed in the United States, which is the 445. But if you look at other countries like in Europe, they are still marketing the 385 and they have the 495. So each tire, it has a little different kind of damage. Yep.
But most of the top-down cracking we see is on thicker pavements.
And that's the whole intention of building the perpetual pavement, because you wanted the damage to be on the top, so you can go ahead and mill it and replace. And what we found here is that the damage that you're getting from the white base tire is less on the upper layer when you have thick pavements because of the uniformity of the load. So you have similar tire pressure, but also you have more uniform load because of the structure of the white base tire. So there's more things involved than just one tire is that size and the other one is this size. There's a complete different structure for both tires.
So you use a different distribution depending on the thickness on the surface?
No, we are measuring the tire contact stresses, and that's what we are applying, and that's the same one is applied for thick and thin pavement. But remember, the contact stresses that you have is different between white base tire and dual tire. So what we are using is what we are measuring.
So white base tire in general has a less tendency to have the surface cracks and the shear happening.
I would say by what, correct me, Jaime, 10%? You did a thick one. It's maybe 10% for the surface and salt strain on the surface and the vertical shear strain next close to the surface. Yeah, something like this. I mean, from all the previous ones. Yeah. It depends, of course, on the pressure and the load and so on. But general, I'm saying 10%.
Yeah, one other thing, I guess, all the dynamic finite element analysis and, to the detail with the contact stresses, how do you bring some of those conclusions into building or developing adjustment factors for MEPDG to take care of white base? So
If you have like basically counting all model complexities in one adjustment factor.
there may be several
Change
other.
MEPDG.
Change yeah.
That's complete.
You know, that's the thing is, I think, Carol, if I may, I mean, he touched on very important points from the first beginning. First, that MPDG, they are using the circular load, they are using the uniform pressure, all these things. So you cannot address them all one by one. So that's why the idea of two adjustment factors, one for the white base and one between finite element and the elastic method.
And think about it, there is calibration factors on top of it. So whatever you do,
Oh,
they're going to apply calibration factors,
Transfer
right?
functions.
Not the transfer functions, calibration factors.
Oh.
A part of the transfer functions, yeah.
Well, eventually the shift factor.
Would the top-down cracking module work then if you had these strings?
I don't know. I mean, it depends who you talk to. I'm one of the people who doesn't believe in top-down cracking, so I wouldn't say yes.
You don't believe in it?
No, I do believe that it's near
No,
the
they-
surface because it depends. Most of the time, it's close to the surface,
Yeah, whatever you
and
call
then it might happen the surface if you have really aged pavement and so on. But mostly, it might happen close to the surface. So the answer is depends on the terminology you're using. So if we are agreed that the top or near surface is the same, yes, I do believe in it, of course.
Well, actually, on that, now this has become a good discussion.
Yeah.
I guess with June's work and going back
to
to
sound flea now.
I'm not going to retake back your thesis.
no, the top-down cracking. I guess June was showing the shear strain being a major problem on the surface.
Yeah, of course.
But now I see Erman is talking more tensile strains and things.
It
So-
depends what data you're looking at. Yeah. So,
The strain plots look like a shotgun.
but, yeah, that question to you.
It's very low relation. Oh, so any other question?
Just one thing of interest to you, Errol,
Sure.
that Erman was discussing this with me like a week ago or so. If you remember in the Tensar project, we were looking into the strain that whenever you have a very thin pavement and very weak subgrade, the problem is the response that we were getting was way, way much more than what we were expecting from the finite element. And this kind of change,
You mean what we measured was?
yes, and this kind of change was diminished as we're going to a thick pavement, even including the ones here at that time. And the only explanation is, I don't know now how much we're going to have trust in the strain gauge measurements when you have it in a thin over weak pavements, because it was bending more than tensile. So, and they were not manufactured to bend. So anyway.
All right.
But yes,
Any
guys,
other
before
questions?
you leave today, I mean, there was a big plan from Angela's parents to have her in the Falls Day on April 1st, but it didn't work. She refused to come on April 1st, and she came on April 2nd. So today is Angela's birthday, so we have some cupcakes, courtesy of Jaime. So happy birthday, Angela.
Thank you.
Now, she is, now Erman's looking